Yo. Number, I'm so sharp, it's a directed inference. This is numbers with same consecutive difference. Let's go ahead and get right into the problem. So you're given two integers, n and k, and you're going to want to return an array of all the integers of length n, all right? All the integers with length n where the difference between every two consecutive digits is k, okay? You may return the answer in any order. All right, so is it length n in each number is different, or is each digit within the same number different? Note that integers should not have leading zeros. Integers such as 0, 2, and 0, 4, 3 are not allowed. Okay. So for the example, we have n equals 3 and k equals 7. And our answer apparently is 181,292, 707, 818, and 929. So why is that the answer? Well, these are all length 3, right? There's 3 digits in this number. There's 3 digits in this number. There's 3 digits in this number, 3 and 3. And the difference between two consecutive numbers is not 7, but the difference between each of these numbers, right? There's a k equals 7 difference here. There's a k equals 7 difference here. A k equals 7 difference here, and so on and so forth, right? Because the difference between 2 and 9 is 7. The difference between any two consecutive digits in the system. 8 and 1 is 7. 7 and 0 is 7, right? So how do we go about this problem? Well, I think the easiest way would be to just enumerate all possible numbers by flowing through the system. And what I mean by that is, well, first thing you got to think about is, well, what are the states that I could have, right? What are all the solutions that I could look at? Well, for the first number, since we have a 3-number system here, right? The first number can't be 0. Because 0, 2, and 0, 4, 3 are not valid solutions, right? Because they can't start with 0. So for the first number, we have 9 options, right? You could have 1 through 9 in this first slot. So that means when I'm looking at this system, if I wanted to think about what could go in this spot, well, 1 could go in this spot in the first slot, or 2, or 3, or 4, or 5, or 6, or 7, or 8, or 9. All right. Now, what can go in the next slot for any number? Well, for k equals 7, it has to be a number that's 7 away. So for k equals 7, I could try two things. I could add 7 to the system, or I could subtract 7 from the system. Well, if I add 7, I get 8 as the next option. But if I subtract 7, I get -6. So that doesn't work, right? I can't subtract 7 and get something good. Same here, right? I can add 7. If I subtract 7, it doesn't work because I get a negative number. For 3, I can add 7. It becomes greater than 9, right? Because I'm talking about each individual digit, right? Each of these columns, if you will, represents a single digit. So I can't have a negative digit, right? My only options for the second digit and there on forward is 0 through 9, right? For the first digit, it can be 1 through 9. It can't be 0 because you can't have any trailing or leading zeros, right? You can't have any zeros leading, right? Your most significant digit can't be 0. So the only thing you have for your first options are these first numbers. And then from there, you can either add 7 or subtract 7. And when I'm saying add 7 or subtract 7, you can either add k or subtract k. And sometimes when you try to add 7 or subtract 7, it's not going to give you a number that is valid, right? Because the digit has to be constrained between 0 and 9 from this point forward, right? So for 3, you can't add 7 because you'll get 10, and you can't subtract 7 because you'll get something negative. So there's nothing for 3 or 4 or 5, right? Because if you add 7 to 5, you subtract 7 from 5, you get nothing good. You add 7 to 6, you subtract 7 from 6, you get nothing good. Well, at 7, you can go the next number 0. You can't add anything. From 8, you can do the next number 1. You can't add anything. From 9, you can make the next number 2. You can't add anything. So now we have information about the second digit, right? And then now from here, what can we do? Okay, I can subtract 7. I can't add 7. I can subtract 7. I can't add 7. just going down through the system, I can add 7, I can't subtract 7. I can add 7, I can't subtract 7. I can add 7, but I can't subtract 7. So now if I just enumerate all these solutions from this point, well, I have 181, 292, 707, 818, and 929. Now, I did this really quickly, so I might have forgot some things here. But no, look at 181, 292, 707, 818, and 929. And just one hint about when you approach these problems, sometimes, not always, but usually it's a good signal that you have the right approach if the solution can be returned in any order, yet your approach returns in that same order. So you are likely approaching the problem in the same manner of which the solution approaches the problem. So that can sometimes be an indication that what you're doing is correct. But that's besides the point. So now you have this kind of tree where what you basically do is you start with these 9 values as your first value, and you just cycle through until you get n values. And every time you get to n values, you just return those n values that you get. Okay? So for any node x, if x is valid, okay, just a generalized argument here, right? You're going to have this whole tree that comes before it that gets you to If you're going to draw a generalized graph, it better look good. Okay. So you have this whole tree to get you to this last digit x, okay? Now there's 2 possible solutions you could get. You could get x minus k as this next node, or you could get x plus k for this next node. Only if x minus k, the difference between x minus k, x minus k has to be less than or equal to 0, less than or equal to 9. X plus k has to be less than or equal to 9. Right? If that's not the case, then it's not a solution, right? For example, here, we can't subtract 7 from 2 because it's not within this range, right? There's this predefined range for what the next digit can be, right? Because there's what the next digit of the system can be, if that makes sense. So at the end, you would just grab this path, whatever that path is. Maybe this is a path. Maybe the path keeps going, whatever. Okay, so the candidate way of doing this would be to run breadth first search, and we add this to our queue, and then we look at all possible neighbors. We look at all possible neighbors, and we keep expanding out the tree using breadth first search until we get an n length system, right? Until we get to that level, right? Because this is level 1. If we ran breadth first search, what would this look like? If we ran breadth first search, right? Breadth first search is a level order traversal algorithm. So if you did breadth first search and you thought as the number of values you've looked at, like the length of the number that you're building, right? Like when you end up, you have a length 3, so it starts with everything that's length 1. So if we started with everything that was length 1, so this would be level 1 of your tree. Let's do yellow. So we look at everything here, and then we'd replace it with everything that we can fill it with. So we replace it with 1829, right? We'd add everything in this system here. So then your tree would be 1829708192, and then you'd do everything in the next level, like that. So this is traversing out tree, okay? So let's go ahead and do that using breadth first search. So we're going to create a queue where the queue is what we're going to be using to traverse the system. And the values that the system can start at are 1, 2, 3, 4, 5, 6, 7, 8, 9. You could use range here or whatever. I'm not going to be that cute. And then you're going to expand the queue by building this tree how many times? Well, you're going to go n-1 levels because you've already populated the first value in the system, right? Like you've already populated that it could be 1, 2, 3, 4, 5, 6, 7, 8, or 9 as the first value. And then you're going to add in a subsequent value, and you're going to do that. You're going to add 2 additional levels, right? Because you're going to go 2 additional levels to get to 3 digits. You're going to go to another level to get 8 and another level again to get 1. So you're going to go 2 additional levels to get a total number of levels 3. So you're going to do n-1. So 2 times you're going to run this algorithm. And then you're just going to update the queue. So you're going to take a number that's in the queue, multiply it by 10, and add in the neighbor. Why are you going to do that? Well, if you have this system here, right? If you thought about what this system was, you have 1 here. And then when you look at 8, you're going to have 18. So how do you get from 1 to 18? Well, you take whatever your previous level was, right? You multiply it by 10, and then you add in the current digit that you're looking at, right? So if you have 1 to 1/8, how do you get that? Well, you take 1 times 10 and you add 8. And then when you have 181, well, at that point, you'll have 18. Right? At this point, you'll have 18. So how do you get from 18 to 181? Well, you do 18 times 10 plus 1, because that'll give you 180 plus 1, which will give you 181. So multiplying by 10, since you're in a base 10 system, we'll just shift your numbers over 1, so then you can add in that newest number. Okay. Well, so we'll use that prev and cur idea, I guess. So we have prev 10 plus cur. Now you're going to look at cur in range. So okay, what's the range for k? So k can't be anything less than 9. Okay, so 10. So we'll look at all the options for all the prev in our queue. So we'll look at everything that's in our queue at the current level, and we'll try to add in cur. But we'll only add in cur if the absolute value of cur minus prev equals k. Right? So we're basically saying we'll check every single digit that we could add, and only if that difference between the current last digit and this value equals k will we add it to the system. That's basically saying, stated another way, what that's saying is, if you have 181, 118, I'm trying to figure out what could my neighbor be. Well, there's only 10 things that I can add. Well, can I make it 180? No, because that difference is 8 here. Can I make it 181? Yes, because that difference is 7. So I'm just basically checking each possible next digit and seeing if it's valid, right? So I'm checking all possible things that could be the next digit, 0 through 9, and checking if they would meet the conditions such that k is the next value, right? So, and another way of saying that is, for any of these nodes, what I'm really doing, instead of just checking 2 things, right, if I had 2 and then 9 here in this system, I could check 2, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And I'd say, okay, does 290 work? No, because the difference isn't 7. 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 So then I know that this would be the only valid path, and I'd add that into my system. Okay? And then at the end, we just return the queue, right? Because the values in the queue will be all the nodes that have that difference. Prev minus cur. Okay, guys, I got to get out of here because I got to go get a haircut. Because I got a big meeting at work tomorrow. What's the runtime of this? Well, you go n forward, and you only create as many too, so just n time algorithm. All right, peace.